So this is our penultimate ID at the seminar series. It's my pleasure to introduce today's speaker, Dr. Nicholas Reich. Dr. Reich is a professor of biostatistics at the University of Massachusetts Amherst School of Public Health and Health Sciences. His research focuses on infectious disease modeling, disease surveillance, and statistical methods for evaluating public health interventions. He's also known for his commitment to reproducible science, clear scientific communication, and effective data visualization. Please join me in welcoming Dr. Reich.
Thanks, Alaric, for the introduction. Thanks to you all for coming today to hear my talk. So I'm just going to give a little bit of background of the work that my research group does and some of the context that I bring to this talk. So since 2011, I've been a faculty member at UMass. My group does a lot of work in collaborating directly with state, local, and federal public health agencies. Early in my career, we did a lot of work with the Thailand Ministry of Public Health. More recently, it's been a little bit more US focused, working with CDC, Massachusetts DPH, a bunch of state and local public health authorities in Texas as well, and throughout the US, in part thanks to funding that we've received through the Center for Forecasting and Outbreak Analytics through CDC. And one of the big cornerstones of the work that we've done in the last, say, 8 years or so, starting a little bit before COVID, is working on these collaborative forecasting challenges. So these are challenges where groups get together and try to make short-term forecasts of the flu season or of COVID or RSV or other pathogens. These happen to be so there's been a bias recently towards these sort of respiratory viruses, but we've also been engaged in other efforts as well, but that's really been the focus of a lot of these efforts. And then early in COVID, we started supporting the CDC through building the COVID-19 Forecast Hub, which became the sort of authoritative source of forecasts that CDC used throughout the pandemic. This project is still running, although we've sort of handed it off to the CDC, and now they're in charge of it, although we're still building the infrastructure behind the scenes. So what this has meant is that in addition to a lot of the scientific work that we're doing and the modeling work, we're also doing a lot of operational work and sort of software development work around supporting these real-time modeling efforts. And this is just a screenshot of one of the dashboards that we host for the Flu Site Challenge, which is the annual CDC-run forecasting challenge. And so we do sort of this mix of operational and sort of operational work with public health, as well as more sort of statistical and modeling oriented work. I have ended up, I'm going to give just a couple thoughts on ID forecasting. Sometimes people, if you see the work that I do and sort of see a lot of this work on forecasting and being at the center of all this hub work, I think people often leave if they haven't heard me talk or met me. They sort of think, oh, Nick must be the sort of champion of forecasting. He must really believe and strongly in how forecasts work. And really, that's not totally the case. I do think that accurate outbreak forecasts can and should be used to inform public health sort of situational awareness and decision making, but I am a very harsh model critic, and I really feel like this is an incredibly hard problem, and basically the field is failing and has been failing for many years at making good forecasts. A lot of the work we do is on figuring out how to evaluate these models better, how to make them better. I think there's a lot of room to make them better. I think it's a very hard problem to make these models better. But one of the things that I think is an important challenge in this field is that when you ask a model to give you a forecast, you are asking it to make a falsifiable statement about the future. And this is something that gives us an opportunity to learn about whether this model is correct or not, and whether some of the assumptions underlying it are correct or not. And it gives us this this opportunity to confront that model statement with data and really learn about where models are doing well and where they're not doing well. Okay, so with that context set aside, I'm now going to pivot and talk about the topic of the talk today. So I changed my topics in like the last hour. I decided to change based on conversations I had this morning with a handful of folks. I was like, oh, actually, I think the thing I was going to talk about is a little bit more of like my sort of pet data science project that I've been doing for a while. And so what I wanted to switch to was one that was a little bit more focused on thinking about these forecasts in the context of infectious disease epi and decision making. So I dusted off an old set of slides, and it's going to be maybe a little bit rustier of a talk, but I think you all will find it interesting. So the topic of the talk, just to go back to the beginning now, is not what may have been sent out in email, but it is evaluating infectious disease forecasts with allocation scoring rules. So that's going to be the topic for today. So let's start by talking about the anatomy of a particular forecast. So let's say that there's some time t when we're going to make a forecast, and this forecast is conditioned on some available data up to that time t, and it might include the time series here, but also maybe another set of information that's available to that model. That's just other surveillance systems, other signals that are out, other knowledge that you have about the world up to this time. And then a model will create a predictive distribution for the future. So in this case, we're going to say maybe for time t+1 through t+3. And at each of these times, it's going to give you some predictive distribution. In this talk, we are going to assume that these distributions are coming to you in the forecast of a set of quantiles that describe a predictive distribution. So for each of these 4 steps into the future, you are getting a predictive distribution that is described, that sort of can be represented by a curve, that is being characterized by a set of quantiles that give you the picture of the full distribution. This is not the only way to represent a distribution, but it has become a common way. It became a common way during COVID, and it has sort of stuck around for better or worse. So here's a question. I'm going to ask for some audience participation. Which of these forecasts do you think is better? So these are predictions. While you're thinking about this, I'm going to describe the setting. These are predictions of the COVID-19 hospitalizations in 4 large states in the US, leading into the Omicron wave in the winter of 2021 to 22. So you can see the black lines represent the eventual data that were observed. These are daily hospitalization counts. And these on the top row are predictions from one model, and on the bottom row are the predictions from another model. So now I'm going to ask you a somewhat intentionally ambiguous question of which of these models do you think was more successful, just based on what you see here, completely qualitatively.
With the exception of Florida, it looks like the bottom model seems to be performing okay.
Okay.
Are we only using data up to the dotted line?
Well, the models only use data up to the dotted line, but we are asking you in retrospect, with now knowing what we know now about what the eventual observations were, I'm asking you to say, which of these models do you think did a better job with the benefit of hindsight? So Alaric says maybe the bottom model with the exception of Florida. So you don't really like how it was underpredicted here in Florida, but in general, you feel like the other ones seem better.
Wider predictions than the other. So.
Okay. Any other assenting or dissenting views on this?
So you could maybe make the argument that the top ones are more responsible with the data they have up to that point, given that there was less data on Omicron and its transmissibility technologies as those stuff going into European from Delta. So the fact is that there was something in there that it was very hard to enforce. So the top results were what were a sort of counterfactual in the absence of Omicron.
Okay. Also a reasonable view. Any others?
I mean, very naively, I would imagine that it's bad to have an underestimate for hospitalizations. because then you're more likely to be surprised, but you'd rather be over prepared. So from that, it also seems like maybe the bottom row is better, with the exception of Florida.
Yeah, so I like where you're heading with that comment. It's sort of motivating a sense of cost of different kinds of errors, which is a little bit of where this talk is going, right? It's like there's maybe more of a cost to making an underestimate. I mean, there certainly might be cost to over preparing and cost to overestimating as well. And yeah, but that's I think a good point in sort of starting to think about what are the costs of one kind of error versus another. Any other comments? Yeah.
Kind of an insider of this community.
Yeah.
So I didn't want to speak too quickly, but since you're opening the horizon of the conversation in terms of decision making,
Mm-hmm.
I would argue that if we had a question in mind, then we could come up with a more informed assessment of the quality of the forecast, right? Because if under predicting will not trigger decision of staffing, then as you said, there's more cost, right? Whereas if you look at New York City, the spread is so large that it suggests that you could see, I don't know, 800 cases or 5,000, or it's kind of like, well, then, the coverage is good, then the observations fell within the confidence intervals, or,
Yeah.
but the tightness, or as we call it, the confidence,
Yeah.
is a little bit wanting.
Yeah.
Right.
Yeah. So oftentimes these models are trained, if they know what the modeling teams that generate these models know what they're going to be evaluated against, and they know that there's a harsh penalty for not covering the truth. So there's this tendency to sort of make these big intervals that you think are going to have a decent chance of covering the truth. But we certainly have had many conversations with public health officials who are like, this is useless to me. Like you're telling me there's a chance that it might be 1,000 or 5,000. Like what, this is not.
Said that, right?
Yeah, exactly. Exactly. Okay. So good conversation that helps sort of motivate this idea of like how we might use these for decision making and what the kinds of costs that that there might be for different kinds of errors in these models. So I'm going to detour for just a second and introduce one of the scores that has become a commonly used score in the community. It's a weighted interval score. And this is basically a way of taking a set of quantiles and coming up with a measure of distance between the distribution and an observed outcome. And so here we have a figure that sort of illustrates some of the properties of the weighted interval score. It can be thought of as a generalization of the absolute error, and lower scores are better. So here is a situation where we have a low dispersion forecast. So there's not a lot of the forecast distribution is narrow and it's centered right on the truth. So here we have a weighted interval score of 2.1 and an absolute error, which is just scoring the point prediction is 0. Here is a situation where we have an incorrect location. So the forecast distribution is not centered in the right place, but it still has a tight distribution. Here are the corresponding weighted interval scores and absolute errors. And in a situation where you have a high dispersion distribution, but correctly centered, here are the corresponding weighted interval scores and absolute errors. So you can see that the predictions are being penalized a bit for being wider here. Like if you compare this, the low and the high dispersion, it's being penalized for being wider and not being uncertain. But here it's being penalized for being too overly certain and not being close to the truth. So you can see there's a trade-off that this score is giving, and it's a very specific trade-off about sort of uncertainty in your intervals covering the truth versus being close to the truth. I don't think we show the actual math behind this, but you can look it up, and it's a fairly straightforward thing. So in this particular setting, here is the correct answer for this one metric, but not necessarily the correct answer with a capital C. It's just like one correct answer. In this particular setting, the CU select model had a worse weighted interval score, in part because it's, basically none of its intervals or very few of them covered the true observation, so it's going to get penalized for that pretty harshly. And the point estimates are a bit further away in general than the JHU APL Bucky model. So the JHU APL Bucky model has a better score by, looks like, about 10%. So here now, this is just I very slightly changed the problem here on this. If you'll notice, I've changed the y-axis is different. So here, what we are showing are not the incident hospitalization counts, but the proportion of daily COVID hospitalizations. I think across, I think this is basically like the proportion of all COVID hospitalizations across the US that are occurring in this one location. So so we're basically saying, like, on this day in California, 25% of all hospitalizations in the US are happening in California. So it's kind of asking, sort of showing on the same scale, the relative size of these these outbreaks across all the states.
Yeah.
Some to
Right. So maybe 0.2%, because otherwise if you sum only those 4 states, we would have 25%, 25%.
Yeah, so maybe it's just across these 4 states and not across all states altogether. Yeah, yeah. So does this change the answer to your question if we reframe it like this?
Because it's exactly the same time interval, it's just visualized in a different metric.
Everything is exactly the same. We've just transformed the y-axis to say, if these are the only 4, so yes, if these are the only 4 locations we're forecasting for, and you're trying to make a decision about, you're trying to make some decision, which of these forecasts now looks better?
It depends what they're trying to do. If they're trying to allocate funding that you've already decided to appropriately top line, but as we saw previously, you would probably get the scale of the funding that was actually required wrong, because of the fact of the deficiencies that the last slide.
Yeah, so there is a question of if you have like you're saying if you have a fixed resource and you're trying to allocate it among these things.
X many dollars which you decided you need to allocate to these aspects for COVID response, this is better. But if you want to decide what X is, previous, the lucky models better. Yeah.
So once again, we're driving towards this thing of like the question that you're asking is important, and that's true. So I'm actually not going to answer this question yet about which model was more successful. We're building to that. But this leads to one of the main points of this talk, which is that we have all these common ways of evaluating forecasts, and I've listed a couple of them here. The log score, this WIS, which is equivalent or is sort of an approximation to a commonly used the continuous rank probability score, CRPS. We think about empirical coverage rates. So these are common ways of evaluating forecasts, but do these align in some way with common uses of forecasts, like just developing situational awareness or communicating what's happening to the public or to decision makers? We might think about planning expansions of hospital bed capacity. We might think about selecting sites for vaccine trials. We might think about allocating a limited resource. These are all possible things that a forecast could be used for. And we don't really have a clear understanding of how these existing metrics for forecast evaluation map to, are these metrics rewarding forecasts for helping us make these particular decisions? And the answer is we don't really know. Yeah, question. This is a great question. So I would say that they're not terribly arbitrary. They are sort of commonly used metrics for scoring probabilistic predictions. The log score is a commonly used thing. CRPS is commonly used. So I think basically it was like, what are things that are commonly used? Here, these are some things that are commonly used. Before COVID, people were using log score because forecasts were represented in a different way. Now more people are using WIS. This represents a like intrinsic shift in the kinds of like utility functions that are underlying them, that nobody has really thought deeply about that.
Simple comparisons to say whether forecasting well defined or well what's happened scoring rules. This is not really designed with any particular objective in mind.
Yeah, I mean, I don't know enough. I would like occasionally dip in and out of the weather and climate forecasting stuff, and I don't know how much they've thought about this. But I would agree. I mean, this is like part of this talk is like a call for help for us to be thinking more carefully about this, because I think it's an important piece.
So for weather forecasting, people have thought about this very thoroughly.
Yeah.
But the clear difference is that they have a lot more information, and namely from measurements, from past experience, there is a mechanistic physical way to map variables onto dynamics. And so whereas I would, for somebody who has never done this forecasting, the number of epidemic outbreaks that we are using to assess anything is very limited for very limited locations. So we are working with small numbers, and yet we're asking probabilistic questions on fewer than 100 observations in terms, if you're asking for a peak, for example.
Yep.
Right. So I think that's another challenge that we have in the community.
Yeah, that's true. The number of things that we're predicting are much fewer than like tens of thousands of weather, measurements from tens of thousands of weather stations and that sort of thing. Yeah. So the main point of this paper, which I'm driving to, which I'm going to try to find some time to introduce some of the key ideas behind, is this allocation score. So this is describing a paper that my group published a few years ago, where we said we think this is a problem. We're going to develop a score that, in a fairly simple idealized setting, can score forecasts based on allocation style decisions that are made using those forecasts. And so we argue that this is like one of the first times that we've said, here is a decision that we want to make, and here is a metric that aligns with that. Not the first time overall, but first time in this field, like this field that people have been making forecasts for 10 and plus years, and there has not been a lot of this like specific mapping of here's a decision and here's a metric that we can really judge how we are at helping inform that specific decision making. Okay, so I'm just going to give a little bit of a background on scoring rules and then describe this allocation scoring rule. So a forecast gives a distribution we're going to call capital F. And later we observe some observed data Y. And the question is, how successful is this forecast? Was the forecast that we reported at this at predicting this thing Y. So we talk about a scoring rule, which we're going to call capital S, as a function of both the distribution F and the observed data Y. And this is a function that assigns a score to a particular forecast when given this observed data Y. We're going to assume here for this whole talk that lower scores are better. This is not uniformly the case, but you can always reorient them. Lower scores are better. And there's a concept of a proper scoring rule that we're not going to get into too much. This is really a thing that like gets into the detailed mathematical properties of scoring rules, but these are important because, especially when you're trying to ask people to give you forecasts about a thing, basically the fundamental idea behind a scoring rule is that if you believe that F represents the best guess at what the truth is, that a scoring rule would never incentivize, a proper scoring rule would never incentivize you to change that. That there's never going to be any way to like game the system by modifying it a little bit or putting a little bit more weight over here or adding a little bit of weight to the tails. You can't, if you think F is what's going to be observed, then you always should stick with F. That's the intuition behind it. There's a lot of math that I'm not going to show you about that, but it's an interesting idea, and this helps align a lot of the more theoretical work that's been done in around forecast evaluation. Okay, so now let me introduce to you the allocation score. So this is a recipe. We did not come up with this recipe for building forecast evaluation, but again, sort of bringing this and sort of mapping it into this infectious disease modeling and forecasting world was a new thing. So the setup is we have a decision maker who needs to select some action, and we're going to refer to this action as X. And the quality of a decision can be quantified in relation to some prediction, like we talked about before, in relation to the outcome Y. And we don't know what Y is at the time that we have to make the decision, but we have a forecast F that of our unobserved outcome Y that is available. And so the idea is we can make a decision based on F, and that decision will allow us to take this action X. So what we're going to define is, so this recipe will give us a proper score. We define a loss function that is a function of a action X and an outcome Y. And so if you take this action and you observe this thing, what's the cost of that action that you took? We define what is called a Bayes act. So this is basically if you've given a probabilistic forecast F, which action minimizes the expected loss under that forecast distribution. So we're going to call this action that is motivated by the action X that is motivated by your forecast F as X to the F. And then we can score the forecast with some scoring rule, which is so the scoring rule, remember, is a function of the distribution and the observed outcome. And but that scoring rule can be basically we can say that is going to be the loss function that we defined in the first step, where instead of it's just the distribution, it is now the action that you've taken as a result of having this assumed distribution and the observed outcome. So this is the observed loss if you took the action suggested by your prediction. So here is our sort of toy example for an infectious disease problem. Let's say our question is we want to allocate K units of resource. And in this case, at least for the first part of the talk, we're going to think of K as equaling 15,000. And we're going to, again, in our toy setup, we're going to think of this as like ventilators, that there's some national ventilator stockpile and it needs to be allocated across the US. And so let's say we have 15,000 of these ventilators, and we need to allocate them across N healthcare facilities or states or something like this. So again, so here our X, this decision that we're making, the action that we're taking, is a vector of integers that are required to sum to our resource constraint. So we're going to make a decision to allocate a certain number of ventilators to each of our locations. And the observation is going to be the observed need. How many ventilators did each of these locations need? And so this Y is, again, the thing that we end up being able to observe. The X is a decision that we could make. And the capital Y and capital F are these, capital Y is this like random variable representing this future need. And F is the forecast of the resource need. So I'm going to skip the slide. So for step one, we want to define this loss function. Here, again, this is like part of this is a little bit of a toy example, but this is a place where like you as a practitioner or talking in conversation with a public health agency, you could define your own loss that reflects the cost in your setting. What we're going to say is that if the realized need in location I is greater to the number of resources that you've allocated, then that's a cost. We're going to say if it's less than that, there's no cost. So if you have allocated too many ventilators, no cost. In reality, probably there is some extra inefficiency in the distribution pipeline, but we're just going to say that's fine. But if there's a need, if you have people who need to be on ventilators and you don't have enough ventilators there, there's a cost. And we're just going to say that the cost is however many the unmet need in that location. So you could throw dollar signs on here and so on. We're not doing that. We're not, and we've simplified the problem mostly just for tractability and getting a first pass at it.
And you're assuming that you have enough resources for the need whenever it happens.
No, not necessarily. So, well,
Because if not, then you will be penalized. So if there are more cases in a location, fine, so the solution would be just to minimize that, but you will always be at a loss, right? Like.
yeah. So if we assume K is 15,000
Mhm.
and
And the sum of the Y's or whatever.
some of the Y's could be greater than or less than that. And so sometimes you end up with allocation if the number is truly quite a lot lower, you often end up with allocation scores that are 0 because it just doesn't really matter where you send them. If the number is a lot higher, then everybody ends up lower. And I'm going to talk a little bit about we do an oracle adjustment where we basically say if you knew perfectly where to put all your resources, could you have gotten it right? And then but would you still be under because you need 100,000 and you only have 15? And so then we're sort of like, what is the avoidable unmet need? I'm going to describe that in just a couple slides. So here's an example, a simple example. Say we have 2 locations where K is equal to 10. We have 10 units of resources, and we allocate 2 and 8 units of this resource to locations 1 and 2, and we eventually observe Y, which is a need of 1 and 10. So in this situation, we have 1 unused resource in location 1 and 1 used resource, and we have 8 used resources in location 2, and we have 2 resources in location 2 where there was like an unmet need. So in this case, our score here is 2. We have 2 units of unmet need. So the second piece of this part is how do you find that vector of allocations, that XF, given a probabilistic forecast F. So again, we find this Bayes act. So this is the allocation X that minimizes this expectation here. And basically this is answering the question according to this forecast, like assuming that the forecast is a representation of what ends up happening, which allocation will result in the smallest expected total resource shortage. So that's the allocation motivated by a particular forecast. In practice, this corresponds to you have all these predictive distributions for these different locations, and you sort of pick one quantile and you choose the number of resources across all of those distributions that is at your resource, at the resource threshold. So we're going to allocate all available resources, and we assume that the probability that the need will exceed the available resources is the same across all of the locations. Okay. So here is a figure that I'm just going to take a minute to explain. So here is resources allocated to location 1 is the x-axis, resources allocated to location 2 on the y-axis. So this line here, the solid black line, represents all allocation strategies where you're allocating exactly 10 resources. This should in some way be discrete, but we're just sort of treating it as continuous. So this is all, if we have 10 resources to allocate, all of our solutions are along this solid line. And these blue lines represent a fixed, before I get to the blue line, the shading behind things represents given the forecast for these 2 locations, the shading represents my expected loss or the expected unmet need if I were to pick a specific resource allocation strategy. So if I were to pick to allocate 2 and 2 resources, then my expected loss looks like it's around 3.5 or so. And if I were to be able to allocate 10 resources to both locations, my expected loss is close to 0. So this is the shading is conditional on my particular forecast distributions. And the blue line represents a level set. So these are capturing a sort of contour in the expected loss space where that's the same value. And so then the solution to this is the place where that contour hits the where there's like one point where it hits the resource allocation. Okay, so the final step of our recipe is to then turn this to take this allocation score and think about it as a score for based on what we eventually ended up observing, and that then becomes the allocation score. So getting back to Mauricio's comment about sort of adjusting for when you're inevitably going to not have enough resources. So basically, we say what we'd like to know is, could we have done better than the allocation suggested by F? And so what we do is we define this idea of avoidable unmet need. And so we say, what if we had an oracle forecast that could just know exactly the right number of resources to give to every location? And we define our the eventual allocation score is actually defined as our raw allocation score from our forecast minus the score that would have been achieved if we had given every location the right number of resources. So back to our simple example here, in this example where we have k equals 10 and we have 2 locations, the raw allocation score here is 2, but since the total need is 11 and we only had 10 resources to distribute, even the best possible allocation has a score of 1. And so the avoidable unmet need is 1. That is the avoidable loss. Our forecast suggested to allocate things in a way that would have had 2, but even the best forecaster could have only avoided 1. So the avoidable unmet loss is 1. Okay, so here's just like the recap of the allocation score. The question is, how should we allocate these k units across n locations? We have a decision, x, a resource need, y, that we eventually observe, but is not observed at the time where we need to make the decision. And in each location, we can use this idea of a Bayes act to set a choice of a resource allocation where all of those resources add up to our constraint k. And so we now have this allocation score that measures how much avoidable loss resulted from using this particular allocation strategy suggested by our forecast. Okay, so now I'm going to move on to a couple quick applications to sort of move us away from the land of the abstract letters and try to tie this to a couple applications.
Can I ask something?
Yeah, sure.
So you spoke of the oracle, right? And so to your knowledge, Nick, say today we had a new outbreak of COVID, right? And we knew how many cases there are this week. How frequently does resource allocation happen at the governmental level using this kind of, which is an optimization, would be extremely simple for observed points? It's no longer a forecast. It's just what it is, right? Because I suspect that we're far from allocating resources, even though we know where there is a need, right? Do you see where I'm headed?
Yeah, I mean, a couple of years ago, I Robbie Goldstein, who's the commissioner of Mass DPH, came and had lunch at UMass, and I ended up sitting next to him at lunch, and I was talking about this project because I was in a moment of working on it and thinking and being excited about it, and um, he so we talked about a couple instances sort of in his daily activities where where sort of resource allocation is done. He was facing a situation where they had like 1 million face masks that they were trying to figure out how to distribute these. This was sort of in the wake of COVID. People were still kind of wearing masks, but not really. Um, and so like, how do they distribute them? We were talking about Mpox vaccines a little bit, another important question. So there are, I think, examples where, the ventilators may not be a great example because you probably are not like, putting ventilators on planes and sending them across, although maybe in an extreme case that probably happened a little bit in COVID.
They were following an algorithmic approach or no?
Oh, I see.
This is suggesting, forget about the forecast. How should you allocate today? Because this is assuming that if we knew we would do this, but now we know what's happening, and based on that, are we changing the way we allocate? So the question is now you asked you ask this question
Yeah.
to the commissioner, and when he decided to allocate the masks, did they follow a formula that minimized the realized cases?
Right. My impression is that people are not making these decisions, certainly not based solely on algorithms, possibly with the help of model output. But, we talked about the Mpox vaccine allocation, and he said largely they had been distributed on a per capita basis, just like population by population.
Yeah.
And not by, they were being distributed by case numbers, which he was arguing against. He felt like they should be distributed on a per capita basis because you don't know, like the surveillance systems are really good in some cities and not in others. So if you distribute them by case numbers, you're essentially rewarding places that have good surveillance and penalizing places that don't have a lot of detection, which was and is a problem with Mpox. So anyway, I think this is it's complicated, and what that example showed me, that specific example about the allocation of these vaccines, was like sometimes a model, this is not a model answerable question if you don't have the data, if you're relying on data that is sort of unseen, or maybe it's a model answerable question, but it's not a straightforward based on observed data. You have to do a lot of inferring of not just the tip of the iceberg. Okay, so I'm going to move on to a couple quick applications. So using this example of thinking about ventilators and allocating federal resources to the U.S. states. So here is a figure showing the Omicron wave across the U.S. The solid black line is showing the time that we were asking for a forecast, and the dashed line is saying, let's, sort of giving ourselves 3 weeks. So we're saying, all right, if we're trying to make it, again, this is all hypothetical, right? Nobody's actually using these forecasts for this. But if we're trying to make a forecast, if we have 15,000 ventilators we can allocate at this time, at the solid black line time, and then we're going to be able to allocate them in 3 weeks time. This is the setting. And again, setting K equal to 15,000. So back to that first example, I don't know if you remember the names of those models, but the top was CU Select and the bottom was JHU APL Bucky, and JHU APL Bucky had gotten that trophy for having the best score of the two. But if you look at this from an allocation perspective, that model on the top gets the best allocation score and sort of a middling weighted interval score. So here is CU Select, the best allocation, the best avoidable loss, but its weighted interval score is 133, which is maybe fourth or fifth or so. Similarly, the JHU APL Bucky gets quite a bad allocation score. It's like third from the bottom, but has quite a good, I think maybe second from the best mean weighted interval score. Here's another model, this USC SIKJ alpha. These model names are sort of atrocious, but that had a pretty good score for both of them. I think I have enough time to unpack this figure, so let's go for it. So the setting here, each one of these little plots is showing one state. Here's the data that was made, the vertical black line again. This is the moment that we're making a prediction. The gray data is the data that was not observed up to that time, and the dashed line is the moment that we're making allocations for. So you have to imagine these two little thermometer charts on the side are sort of designed to be showing you the allocation that happens at this moment of the dashed line. And so the horizontal red line shows the actual observation. And this is like what the allocations needed here. And on the left, we have the allocation suggested by the JHU APL Bucky model. And on the right, it's the allocation suggested by the CU select model. And you can see basically across all of these big states, the allocation selected by the CU select model is closer to the truth, right? Especially in Florida, it's really quite noticeable. The allocation selected by the red CU select model is a bit closer to this high need here. It's a bit closer in New York. It's a bit closer in Texas. It's a bit closer in California. They both overshoot. They both suggest more resources in Ohio than are needed. Illinois, it's a little bit, but I think the key thing is that it got these did a better job, that CU select model did a better job predicting the resources needed in those 4 big states. Even though it was consistently underpredicting, if you remember from those early plots, it consistently underpredicted, like basically everywhere. But what it got right was some like measure of the relative amounts needed in every state. It sort of got that right. So in some heuristic way, what the CU select model did better than the JHU APL Bucky model is that it like ordered the locations correctly. It sort of got the relative heights of them better. Yeah.
Do you compare the scores to something like a baseline that would be, let's use kind of the proportion used on the previous week to the following, because it seems like the best model now, the CU, is saying like whoever had more, it will be getting more. And because the other ones are also really low, I prefer to not miss the ones that may increase more exponentially than the ones that may increase by a really small amount, because again, my score would be worse, right?
Yeah. I think I'm not sure I fully understood, but I think partly your question. So there is a baseline model in here, which is basically saying at the time, it's essentially like a persistence model, like a flat line off the most recent observation with some uncertainty around that. So that is kind of like a reference point. I'm not sure if is that answering your question?
I was thinking something like that, but instead of putting the same number, I would say thinking of like on the proportion out of all of them. Not of all of the ones that you have, but I think it's a slightly
like a per capita.
Well, not per capita. If you have 10,000 in one, or 5,000 out of 15,000, you put that proportion, not actually the 5,000. Because if for the next one you're gonna have 20,000 available, you want to put the third, not the 5,000. It's like a weight per location based on the total amount that you have on a specific time.
So
I'm not sure.
Maybe I can.
Yeah,
I
sure.
don't know if this is what you're trying to say, Laura, but if you went back a couple of slides where you showed that the CU select was better with the proportion, right? When you had this, it was before, and it was maybe
like far before.
right? Yeah, there. So you go forward now, one more there, right? So basically, maybe, and again, I may be wrong, but if in this metric, if you use persistence in this metric, would you, just right? Because the persistence, my impression is that in the previous y-axis, but if you use persistence in this y-axis, would you? That would be the actual baseline to compare to.
Yeah.
Does that make sense?
Yeah, it does make sense, and we have not looked at that, but that's an interesting question.
Is that so?
I'm not sure, but we can talk about that.
There's an area I as well. Being things like Florida, we expand to latest but later than New York does.
Yeah.
So, and it might be easier to get them there ahead of the flight than to have like flights back and forth from Florida to New York.
Right.
Nick Lincoln is asking, is it fair to say that this is just rewarding relative prediction across locations and is unaffected by global bias in models?
I think in a rough sense, yes, it is true that it is rewarding this like relative scale of heights at this one particular time. And that, yeah, it is not like, CU select in this case was systematically, structurally biased below. And this metric doesn't really care. And it shouldn't, like, it doesn't need to, because its goal is just to like figure out what to do with these 15,000 ventilators. And then for that particular question, it gives a better answer in this one context. There's one other, just like a little bit of history about this project is we have this one paper that was published in Journal of Royal Society Statistics Interface, something like this, or Statistics and Society, something like that. And it's a pretty dense methodsy kind of paper, because that's the authors on this were those kind of people. So we have been working but I keep on having all these conversations with these public health officials, and they keep on saying, oh, we want, these are these kinds of settings. We want forecast decisions that are a little bit more tied to, or how do we tie forecast to decision making? And I keep on being like, oh, you should read this paper, but it's like not quite the right paper to suggest to this group. So I have a PhD student who actually used to work in Massachusetts Department of Public Health, who's been working on a like digestible version of this, and she's been running an analysis, again, using the Omicron wave, but using county level predictions in California to just say, here is like an application of this in a sort of bite-sized way, a much more like little math, emphasis on the application to sort of make this a little bit more of a like, oh, here's this thing that that people could use. So here's just like another, so I'm just going to show a couple slides from that work. Here again, we have we're trying to predict the number of sort of some hypothetical resource that we need. This is the Omicron wave of weekly incident. This is now weekly incident cases in California during the Omicron wave. I think we've maybe excluded LA County because LA County is basically like its own state and actually has its own like resource allocation line. So we were encouraged in collaboration with folks at the California Department of Public Health. They were sort of like, maybe you could even consider LA to be its own thing. So we've left LA out. We've made predictions. We've sort of looked at predictions. We haven't made predictions. We've collected predictions other people have made from 2 different times targeting this one date, and set a sort of resource constraint that is particularly spicy at this one moment to be like, it's going to be hard to get this right. You're going to have some unmet need here inevitably. So here are some of the predictions that were made for just a few of the, I think, 50 some counties in California. You can see, as usual, the forecasts are not quite seeing that uptick. And here are sort of a way of sort of looking across all the counties, showing the under and over allocations made by the different models. This is looking at 3 weeks into the future, how the allocations have missed. Here, we included a per capita allocation, which 3 weeks into the future does not do the best, but is like second from the top. And if you look 1 week into the future, this per capita allocation is quite a bit lower, suggesting that maybe at a 1 week horizon, if you have a decision that you can make quickly to distribute things, actually looking at the data helps you a few weeks out. Maybe just distributing on a per capita basis starts to be a better rule of thumb. I'm going to skip that for time. So just a couple sort of high-level takeaways here. We've developed this novel scoring rule in the context of that it's a hypothetical, a little bit of a toy scenario with a toy scoring rule, but we invite amendments to this and sort of ways to figure out how to make it better and more targeted. This measures different aspects of forecast skill than some of the traditional measures do, and we think that's an important thing. Is you should be looking at multiple different measures to think about quality of forecasts. And also in this original paper, we illustrated this pretty general framework for deriving scores based on specific decision-making contexts, as long as you can quantify that loss. There's a lot of things that are still to be done here. I'm not going to go over all of them, but there's a lot of limitations and areas for future work, and I'm happy to talk with folks about any of this. And I'm just going to end there. Great. Thanks so much.